the single greatest threat to modern civilization is a flicker. A flash of light that holds more power than a nuclear reactor and strikes the Earth 8 million times a day. This is the story of an invisible war. A constant, high-stakes battle fought between our electrical world and the raw, untamable power of the sky. Our entire way of life, our hospitals, our economies, our homes depends on a fragile network of wires and transformers. A network that is under perpetual assault. To protect it, humanity had to make a profound choice. To fight fire with fire. To build our own lightning. By the end of this journey, you will be taken inside the world's most secret and extreme high-voltage laboratories. You will witness the staggering power of man-made thunderstorms, and you will understand, for the first time, how a hidden community of engineers subjects our most critical infrastructure to forces that border on apocalyptic, all to ensure that when you flip a switch, the lights stay on. The question isn't if the grid will be hit, but how it survives the millions of strikes that happen every single day. The answer is being forged in thunder and steel. To understand how to defeat an enemy, you must first understand its nature. And lightning is a far more sophisticated and sinister adversary than a simple bolt of electricity. For centuries, we saw it as a singular, instantaneous event. A brilliant flash, a deafening crack, and then it was over. But when scientists in the early 20th century began to capture it with high-speed equipment, they discovered a terrifying truth. A lightning strike is not an event, it's an invasion. It begins with something called a stepped leader. An invisible, probing tendril of charged particles descends from the cloud, branching out, feeling its way towards the ground in steps just 50 meters long. It travels at over 200,000 miles per hour, yet to our eyes, it's completely undetectable. This is the Scout. It is searching for a target. As it nears the ground, the immense electrical potential of the cloud induces an opposite charge in the earth below. The ground itself reaches back, sending up its own tendrils of plasma from tall objects, trees, buildings, and most invitingly, power lines and transmission towers. When one of these upward streamers makes contact with the downward probing leader, a channel is completed. A superhighway for electricity is formed. And then, the main event, the return stroke. In less than a microsecond, a catastrophic amount of current, hundreds of thousands of amperes, rushes from the ground up to the cloud at nearly 1/3 the speed of light. The air in this channel is superheated to 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun, causing it to expand explosively. That is the thunder we hear. It is the mind-bending speed of this event, the rise time, that is the true killer. It's not just the raw power. It's the fact that a component, like a transformer, can be hit with 1 billion watts of energy in a millionth of a second. No conventional material, no standard piece of equipment is designed to withstand a shockwave of energy that arrives that fast. It would be like trying to stop a bullet with a piece of paper. The energy doesn't just flow, it punches through, vaporizing metal and shattering ceramics from the inside out. Engineers now had the blueprint of their enemy. They knew its speed, its power, its method of attack. They understood the physics of the assault. But knowing what the enemy looks like is one thing. Building a weapon that can perfectly mimic it, that can be controlled, aimed, and fired on command, is another challenge entirely. And it required an invention straight out of science fiction. The Marx generator. Enter the high-voltage laboratory. These are not ordinary rooms. They are colossal cathedrals of science. Vast indoor spaces the size of aircraft hangars, shielded from the outside world like a Faraday cage. The air inside is still, clean, and crackles with a low hum of anticipation. And at the heart of it all, dominating the space, is the generator. It doesn't look like a generator you'd find at a hardware store. It is a towering, skeletal stack of capacitors, resistors, and spark gaps, an intricate ladder of components reaching towards the ceiling. This is the invention of Erwin Otto Marx, conceived in 1924, and its brilliance lies in its deceptive simplicity. It solves the impossible problem. How do you generate millions, or even tens of millions of volts, and release it all in a nanosecond? Imagine a long line of firefighters, a bucket brigade. Each person fills their bucket slowly and carefully from a tap. This is the charging phase of the Marx generator. Each of its dozens, sometimes hundreds, of capacitors are charged in parallel, using a relatively low, manageable voltage. It's a slow, safe, and controlled process, storing up electrical energy bit by bit, like coiling a spring tighter and tighter. The generator might take a full minute to charge, gathering its strength in near silence, the only sound the hum of the power supplies. Then, the command to fire is given. In our bucket brigade analogy, this is the order for every single firefighter to throw their water forward, at the exact same synchronized moment. In the generator, a trigger pulse is sent to the first spark gap at the bottom of the stack. It fires, creating a spark. This spark's light and electrical impulse instantly triggers the next gap up the ladder, which triggers the next, and the next, in a lightning-fast chain reaction. This cascade of sparks effectively rewires the entire circuit. The capacitors, which were being charged in parallel, are now, for a fraction of a second, connected in series. Their voltages add up. 10 capacitors charged to 100,000 volts each suddenly become a single source of 1 million volts. 100 capacitors become 10 million volts. The coiled spring is released. The entire stored energy of the massive capacitor bank is unleashed through a single point, in a focused, directed, and terrifyingly powerful pulse. When a large Marx generator fires, the experience is visceral. First, a series of sharp cracks as the spark gaps fire in sequence up the stack. Then, a deafening, bone-rattling boom that echoes through the cavernous hall. As the main arc, a man-made lightning bolt leaps across a 10, 20, or even 50-foot gap to its target. The air is instantly filled with the sharp, metallic smell of ozone. For a blinding moment, the bolt illuminates the entire lab with an eerie, blue-white light, revealing the immense scale of the machinery. With a controllable, billion-watt thunderbolt at their command, engineers could finally begin the real work: sacrificial testing. But what exactly are they testing? And how do you measure the moment of failure when it happens faster than the blink of an eye? The power grid is a sprawling, interconnected organism, but its backbone is made of a few key components. The most visible are the transmission towers, the steel giants that march across our landscapes. Hanging from their arms are the grid's most vital guardians: insulators. An insulator is a simple device with a profound job: to keep hundreds of thousands of volts of electricity flowing through the wire and prevent it from taking a deadly shortcut to the grounded steel tower. They are typically made of porcelain or glass, formed into a string of stacked, skirt-like discs. That iconic shape isn't for aesthetics. It's a carefully engineered defense. The skirts, or sheds, increase the creepage distance, the length of the path a current would have to travel along the surface of the insulator to reach the ground. In wet or polluted conditions, that extra distance can be the difference between normal operation and a catastrophic short circuit. But what happens when that insulator is hit by lightning? Inside the lab, a full-scale replica of a transmission tower arm is constructed. A brand new, multi-million-dollar insulator string is hung in place, exactly as it would be in the field. This is the target. Across the hall, the Mark's generator begins to whine, its capacitors slowly drinking in energy. In the shielded control room, engineers watch on a bank of monitors. High-speed cameras, capable of shooting 1,000,000 frames per second, are aimed at the insulator. A host of sensors are attached, ready to measure voltage and current with nanosecond precision. The countdown begins. Warning sirens blare. 3, 2, 1. The generator fires. An arc of pure energy, a perfect replica of a lightning return stroke, leaps across the gap and smashes into the insulator assembly. There are two possible outcomes, and they happen in a flicker. The first is a flashover. This is a success. The lightning strike, seeking the path of least resistance, arcs around the surface of the insulator, through the air, and harmlessly to the grounded tower structure. The insulator has done its job. It has withstood the initial voltage impulse and forced the energy to go around it, not through it. After the flash, it continues to function perfectly. The second outcome is a puncture. This is a catastrophic failure. The voltage is so immense, the rise time so fast, that the energy doesn't have time to flash over the surface. Instead, it punches a hole directly through the porcelain or glass material itself. The insulator is instantly destroyed, turned into a conductor. The high voltage line it was holding up is now permanently grounded. On a real grid, this would trigger a major outage, a cascading failure that could black out an entire region. By repeatedly striking these components with varying levels of power and different electrical waveforms, engineers can find the precise breaking point. They watch the ultra-slow motion footage, seeing how the plasma channels form and race across the insulator's skirts. They analyze the sensor data, building a detailed portrait of the component's last microsecond. This data is then used to refine the design, to change the shape of the skirts, to test new composite materials, to add corona rings that help manage the electrical field. It is a brutal, expensive, and relentless process of trial and error, pushing materials to their absolute limit, to find the perfect balance of performance and cost. Hardening a single insulator is a monumental task. But lightning doesn't just make direct hits. It can strike a line miles away and induce a massive surge of voltage, a transient overvoltage that travels down the wire like a tidal wave. This wave will eventually arrive at the most expensive and sensitive part of the entire grid, a substation transformer. You can't make $1 billion transformer infinitely strong. So how do you protect it? You need a different kind of guardian, one that makes the ultimate sacrifice. This is the job of the surge arrestor. If the insulator is a shield, the surge arrestor is the grid's pressure relief valve. On the outside, it looks like a simple ceramic or polymer cylinder, often found sitting next to a large transformer. But inside is a column of small, puck-like discs made of a remarkable material, metal oxide varistor, or MOV. A varistor is an electrical chameleon. Under the grid's normal operating voltage, say 345,000 volts, the MOV discs are highly resistive. They act as an insulator, and almost no current flows through them. But their resistance is critically dependent on voltage. When a lightning-induced surge arrives, and the voltage suddenly spikes to 1,000,000 volts or more, the MOV's properties transform in a matter of nanoseconds. Its resistance collapses to near zero. It instantly becomes a highly efficient conductor. The gate that was closed is now thrown wide open. This open gate provides an easy, safe path for the destructive surge current to flow directly to the ground, bypassing the precious transformer entirely. The arrestor shunts the tidal wave of energy away, absorbing the immense stress. Once the surge has passed and the voltage returns to normal, the MOV's resistance instantly returns to its high state, and the gate closes again. It's a heroic, split-second act of self-sacrifice. And in the Lightning Labs, these unassuming heroes are tested to destruction. Engineers don't just want to know if they work, they need to know their exact limits. Using a combination of generators, they'll hit a surge arrestor with a massive current pulse to simulate the lightning strike, immediately followed by a high-voltage AC current to simulate the grid's normal power flow. This is the ultimate test. Can the arrestor successfully divert the lightning and then correctly extinguish the follow-on power from the grid without failing or exploding? They are pushed again and again until they rupture, often with a loud bang and a flash of light. Researchers study the failure modes, analyzing the fragments of the MOV discs to see how they broke down. This relentless destruction derby allows manufacturers to build arrestors that can reliably perform their sacrificial duty for decades out in the field, silently waiting for the 1 microsecond they are needed to save a city from darkness. Through this relentless cycle of creation and destruction, a new generation of hyper-resilient grid technology is born. But this is a war that never ends. As our world becomes